methods around 05. This is almost 15 years ago, and I graduated in 07, so it's been a while. But now the modern approach that have been used also in collider physics, all this, how did Lance call it? Amplitudology, Lance Dixon, okay? Now those methods, so here we'll see how Feynman diagrams enter in the calculation of gravitational waveforms, okay? And then all this idea of amplitudes is to get rid of the Feynman diagrams and to use unitarity methods and all other kind of constraints that you can have in the amplitudes to compute, for example, cross-sections, so scattering. Can those methods also help us compute or solve the two-body problem in gravity? And in fact, if I have time, these particle physics methods will be a combination of this plus amplitudes. So why am I doing this? Why am I telling you all this? It's just to convince you that it's a very exciting field. Okay? It's very exciting because there is a lot of new methods that we can use to learn about GR. We can even redefine the way we think about general relativity because we're going to use methods which are tailored also for Yang-Mills theories, something like the double copy that you might have heard about, which are ideas that are in Yang-Mills and are being exported to gravity. But also because we have data, and then we can explore physics beyond the standard model with high precision waveforms. Okay, it's a very exciting field, also for particle physicists. And that's why I guess I'm here talking to you. Okay? So what is our goal? Let me just first tell you what the goal will be, and then we'll start with some equations. So as you know, LIGO detected gravitational waves, and the gravitational waves detected by LIGO so far have been binary compact objects. So there are many sources of gravitational waves. We'll study this in general. But the most prominent sources that we will see are binary compact objects, okay? So these are compact objects. They could be black holes or neutron stars. They're orbiting above each other. They're separated by some distance, r. They have some size. That is compact, so this will be, for example, of the order of gm, m is the mass, and they're emitting gravitational waves. And this later is seen by the interferometer. So this gravitational wave, very, very far away from the object, is a weak perturbation of a space-time. And solving for this guy will be our objective. Okay? Now, as you see here, full general relativity. There are a lot of different scales in the problem. So there are the forces that bind the system together, right? There are the internal dynamics, for example, in a neutron star. And then there is the scale of the gravitational wave emission. So of course, when these guys get very close to each other, the general relativity is a fully nonlinear theory. It's very hard to solve. So there are numerical methods that are used. I'm not going to talk about numerical relativity at all, okay? But I will mention some of the results of numerical relativity that are hinting and perhaps some deeper structure in gravity that we might uncover one day, that might allow us to do some analytic computations in the strongly coupled regime. I'm going to concentrate in a regime in which the size is much less than the separation and much less than the wavelength of the radiation, okay? And this is, when you see, if you're a particle physicist, and in particular if you're in effective field theories, the moment you see a problem, you tell me what are the relevant scales in the problem. That's the first thing you need to identify. And are those scales in a hierarchy? Are they separated, okay? And this is the case in the regime in which the velocities compared to the speed of light are small. So those guys are going around each other at some frequency and moving with some relative velocity. If the relative velocity is small, then the scales are separated, and this is what is called as the post-Newtonian regime. And this is what we will concentrate, which is a regime in which we can do perturbation theory in the metric. How many of you have seen some post-Newtonian theory? Now you're not so confident anymore. You're not raising your hand that high. Okay. All right, so this will be what we will do. In this regime, we will be able to do some analytics to solve actually with pen and paper and Mathematica the equations, of course. The moment these guys get very close, this separation doesn't work anymore. We rely on numerical relativity, but as we will see, the majority of the signal for most of the sources of interest will occur in this regime, in the post-Newtonian regime. We will see a lot of the cycles in this regime. If you paid attention to the papers that LIGO put out, where they observed gravitational waves for the first time, the first paper was about the observation of the coalescence of binary black holes. And they used the word coalescence because they only saw the end, and it was mostly done numerically. But the detection of the binary neutron star in spiral, the gravitational waves from the binary neutron star wasn't in spiral, wasn't in spiral regime. It was the detection of the binary neutron star in spiral. In spiral is by definition in this regime. This is what's called the in spiral, as opposite to coalescence. So they only saw this. They did not get to see the very end, nor even the merger. Okay, so most of the information we know about neutron stars, or the dynamics, the internal equational state of neutron star is known analytically. Well, there is some we will see there is some matching to numerical GR to actually have the full waveform, but most of the information came from here. And since most of the information will come from here, you need to know the templates really well. And that means that we need to solve Einstein's equations to high level of accuracy, and this is where we come in. Okay, but as we will see, there are many cycles. There are thousands of cycles in the LIGO band, and we need to model those very well. Okay, so that's going to be our goal. It will be to compute this guy. Essentially, actually, what we will compute, this guy has an amplitude and a phase. So most of the computations that we will see will be in this post-Newtonian regime, in which the binary is emitting gravitational waves, but it's shrinking very slowly, right? So there is a regime in which this is small. The change on the orbital period, on a period, right? The change of the frequency on a period is very small. So this will be like an adiabatic approximation. So this will be in the post-Newtonian regime. I'm supposed to use this, right? So we're setting up the problem, right? And this will be in the adiabatic approximation, in which this is small. Okay, how small we will see. We'll calculate this. This will be one of our goals, right? And in this adiabatic approximation, when we solve for the waveforms in what is called, what is usually known as the in spiral regime, we concentrate mostly in the phase and not so much on the corrections to the amplitude. So we want to know the phase of the gravitational wave very well, because that's mostly what this interferometer is going to detect. So it's the changes in the phase that are going to be measured by also the changes in the interference pattern in the interferometer. So we want to know this evolution of the frequency of the gravitational wave in time to high level of accuracy, and not so much the amplitude. Although in the future it will be important, but mostly we will concentrate in computing the phase. Now, the frequency, which is the integral of the phase. So this guy will be related to the orbital frequency. So if we solve the orbital frequency very accurately, then a leading order at least, this will be related by a factor of 2, as you know, it's a spin-2 field. The gravitational wave frequency and the orbital frequency are related. So if we solve this guy to high level of accuracy, the orbital frequency, we know this frequency that gives us the phase. And from here, we get to the prediction. Okay? How this changes with time, which is associated with the pattern of interference that we see in the detector. So I'll tell you a little bit also about this. But hopefully we know then what we need to do. This is sensitive, the detectors, the LIGO detector is sensitive to the phase, also to the frequency of the wave, mostly, not so much the amplitude. So we want to measure this guy, which means we have to solve this problem to compute how the frequency, the orbital frequency changes with time to high level of accuracy in a regime in which we can calculate. Okay, that's our main goal. And hopefully, we'll see how the traditional approach has been doing this calculation so far, and how these modern methods that we have introduced with this effective field theory approach have had some impact in allowing us to go to high orders in this post-Newtonian expansion, which, as you will see, what is the expansion parameter? That's the other question you need to ask, as we will see. You have 3 scales, so the expansion parameter will end up being ratios of these scales. Now, often if you talk about the post-Newtonian regime, then as you might have heard, what you talk about is an expansion in the relative velocity. So first post-Newtonian correction is order b squared. But what does that mean? Well, it means that there is a ratio of scale here, and that ratio of the scales will be parameterized by powers of b. As we will see, it's very easy to see, for example, if this is a compact object, the ratio of gm over r, the ratio of those 2 scales, is nothing but b squared. That's the virial theorem, right? So the typical potential is comparable to the typical kinetic energy. So even though you're doing perturbation series in the ratio of scales, what you should be doing is this. So it's gm over r, but then there is another parameter, which is r over r, and you're assuming that this is an order 1 number, and this is, you're assuming that this is an order 1 number, and this is b squared. Now you have to be careful about that, and this will be one of the key, this parameter here will be one of the keys about going beyond this, what am I doing, sorry? Not r, sorry. You should tell me when I'm doing something wrong. So this is v squared, but the ratio that we're studying is r over r. So I'm going to put the gm and the gm. This is v squared. Don't be afraid to tell me you screw up. And this is the one that I want to say is order 1. Or just too quick. So this parameter is the one. This r, the actual size, how much bigger with respect to the gravitational radius is a key factor. Because that means that if you do naive power counting, which is power counting will be an important aspect for us in effective field theory, I say, oh, that's going to scale as v to some power. Say you have, if you heard, I mean, don't be afraid if you don't understand what I'm saying, because we will get to this point. But in effective field theory, you always have these high dimensional operators that know about the short distance physics. The same is going to happen here. There will be some kind of short distance physics, and there will be some operator in some effective theory that will describe this. And this will be the way in which we're going to explore this gravitational collider. Okay? So naive power counting will tell you at which order in this parameter that operator will enter. This is what we will do. We will power count. But it could be enhanced by some dimensional ratio. If this R is much, much bigger than GM, then something that you might expect to enter much, much, much later in perturbation theory could be enhanced. Okay? And this is going to happen, for example, with a neutron star. That's why the equation state of the neutron star enter earlier than we expected it. Because R, for a neutron star, I shouldn't put this too close, is actually bigger than GM. And that will enter to some power, and that power could be large. When we compute here, for example, at which order in perturbation theory this will enter, to some n, and if this is 2 or 3 or 4, and it's to a high power, say 5, then you have a large enhancement. And this is how we're going to learn about the internal structure of the objects. Okay? This would be our approach. So important is like, what are the relevant scales? What is the ratio of those scales, which is your expansion parameter? And keep in mind that there are some dimensionless numbers going around that carry information about the UV physics. Okay? But this will be ultimately our goal. How accurately we need to know the waveforms, how accurately we need to solve the two-body problem to be able to be sensitive, for example, to the internal structure of a neutron star. That's a natural question you might ask, because if you don't control the waveforms to that order, then how do you know that you're seeing information from the internal structure, or you're just pure GR? Okay? It's the same as you do in collider physics in the standard model. You need to know your backgrounds really well, otherwise how do you know that you've seen new physics? Okay? And many of the tools that we use in this approach, in this so-called modern approach for gravitational waves, are directly extracted from effective theories for QCD. So almost one-to-one, you will see that the methods that are applied in QCD also apply here. And also other methods as we will see. So understanding your QCD backgrounds is very important if you're going to discover the Higgs. Okay? So if we're going to learn about new objects in nature, how do we know there are just neutron stars and black holes out there? What if there is a new object, a new compact object we've never seen? How are we going to know for sure it wasn't just a black hole? You need to be able to distinguish whether it was a black hole, a neutron star, or something else. A neutron star, we have the counterpart. We have an electromagnetic shock. And then we can see that. Okay, we know. It's not a black hole. But what if we don't see that counterpart? How do we know? Just from the gravitational wave signal, that we saw a black hole or something else. This would be one of our targets. How can we tell what is out there? And then to learn about the internal or the UV physics. It's the same you do in a collider. Okay? But for that, you need to know your backgrounds very well, which means you need to know the GR part of this problem very accurately. Before we include all the effects of the UV, we need to understand the effects of the R and lambda scale first. Okay? So that will be our goal. All right, so now that we set up our goal, let's start doing some calculations. Do you have any questions about this? No, because it's all clear? Or no, because we will see how we calculate? I take the smiles as a positive answer. Okay, good. So now we start doing some calculations. So the idea will be, ideally, what I would like to do, I don't know if I'll get there, but is not only solve the linearized theory, but give you some glimpse, and hopefully using the modern tools, of the first correction to the linearized theory, what is called as the one post-Newtonian correction, to compute, for example, the phase, the gravitational wave frequency that gives us the phase. Okay, so the integral of this is the phase, right? So hopefully we'll get there. I never get there, but we'll see. Because that's once we see the linearized theory, and then we'll see that from the linearized theory, and we look at the LIGO data, we can get almost everything about the first detection, for example. We will see, since I'm here, I also feel tempted to do some Fermiology, which means we can do some Fermi-type reasoning to get almost everything, just looking at the picture. Okay? So we'll see that this almost gives us all the information we need to know about the mass, the distance, and so on, the energy release in the gravitational wave coalescence of the first detection. But as we will see, if you want to get, for example, we can get this so-called shear mass, which is some combination of the masses really, really well. Because obviously, if you have an observable, like the amplitude or the phase are leading order, you'll get some combination of the masses. You will not know them individually, you will know some combination. That happens to be this shear mass. Okay? But how do you know the individual masses? And the spin, for example, how does the spin affect the waveforms? You need to be able to know the waveforms very well to actually tell apart the individual spins and masses. And this will be part of the main goal. Because you want to know what the M1 and M2 are, and the spin 1 and the spin 2 are, and the internal structure as well. Okay? And for that, you need to go to higher post-Newtonian orders, because what's going to happen is that this guy evolves in time, and as this guy evolves in time, very early on it's mostly linear, and then you get this shear mass very well. And as you start progressing, the waveforms of the linear theory and the nonlinear corrections start to matter. And by looking at that deviation, you get the mass ratio. By looking at the deviation later on, as you approach the merger, you get the spin, some combination of the spins. Then as you approach and keep going, you get each one individually. And then as you keep going, you start seeing the internal structure and so on. So if you have a very long waveform and you know it very well, by getting first the shear mass from the early part, then the mass ratio, then the combination of the spins, then each individual spin, then the effects of the what we call final size effects and so on, then you get all the information out. But for that, you need to know this function really well. Okay, and that would be our goal. So the first post-Newtonian correction, if I have time, which I will cover hopefully with these modern tools, will tell us, for example, what the mass ratio is. Once you know the shear mass, you know this combination, you don't know each individual mass, but the first correction has this M1 over M2 in it, so that allows you to disentangle this, the individual masses. There are many degeneracies that are very hard, as you know, when you have one observable, but we have an observable that we can track in time. So that's the new thing. So we have a waveform that we follow in time, and we're going to have a template that we're going to try to match. And by matching that template, we're going to get all the information about where this is coming from. Okay? Good. All right. So now let's start doing some, so let's do some traditional. So now my idea was to tell you what you find in books about gravitational waves, at least for, how much time do I have?
It's about
1
1 hour.
1 hour?
1 more hour.
Ah, 1 more hour.
Usually earlier or?
Can I say, no, earlier no, but I mean later. Well, it will depend. We'll see how much we go.
We should finish by 1 p.m. because we have the lunch.
Ah, okay. Okay. I'll be very happy if you guys are interested, because I don't want to lose too much time on the... You will see things that probably you haven't seen, if you haven't seen gravitational waves. So I want to give you the traditional method, so you can also appreciate why the particle physics method is so much better. If you haven't seen the traditional, how do you know that the other way exists and it's better? But I'll be happy to do that maybe in the afternoon if some of you are interested, so we can actually get to the particle physics part faster, okay? So unless you have a very deep question that maybe I can answer, let's go through this relatively quickly, okay? And if you're completely lost, please come back to me later and we can just review, okay? I'm doing this for you, not for me. Well, I enjoy it, but it's for you. Okay, so GR. I forgot how many of you haven't seen GR. So hopefully it will not be, you will not need to know too much about GR to do linearized gravity, okay? Just trust me in some aspects of it, and then we'll see whether we can get stuck on it. So as most of you know, there is an action for GR, which is the curvature. And I'm going to use, this mostly will appear later. So I'm putting it in here now because later when we do the particle physics approach, then the action is going to come back, okay? So this definition will matter later. And this is nothing but the 16 pi g Newton, right? 1 over. We just write in terms of this M Planck. Now you might ask me, where the heck are the H bars? Why there is an H bar? We're going to do classical physics. Hold on to that, okay? The classical limit is actually quite subtle. And just getting ahead of myself a little, right? Remember, I'm going to erase this, but that actions have units of H bar, right? So the H bar is just 4 units, right? Because there's a classical contribution here too, even though there is a 1 over H bar in front of it, okay? And getting that will be also part of the whole story. And it's a very important part of the story in the amplitudes business, okay? Because the amplitudes are loops. If I do loops in amplitudes, how do I know how to extract the classical limit? And now something that you learn in school, that is loops are quantum, is completely wrong. Loops are not quantum, okay? In fact, the most classical part is a lot of loops, okay, of order S over H bar loops, okay? So this will change a little bit your perception about how you take a classical limit. So for now, hold on your horses about the H bars, okay? We'll get back to that. And this is the so-called Einstein-Hilbert action. And then we have also a piece that this is the total action, which is matter. And this will matter, for example, if you have a neutron star or any other object which is not a black hole. There will be other fields in the problem. But interestingly, and this is one of the deepest things about GR that you may or may not have stopped to think about, this is 0 for black holes. This is all there is for black holes. And I'll tell you in a minute why this is one of the deepest things about GR, and actually about nature, if you think about it even deeper, is that, as you know, we can define or introduce the stressed energy tensor which even, as you know, you can do this trick also if you don't have gravity. You can just take the derivative with respect to some fiducial metric, and you can also define your T mu that way. And the boards, I write big, and the boards are small. Let's see how this goes. So once you have a matter component, you have a T mu, you vary here with respect to the metric, and you get the Einstein tensor. So from here, you get Einstein's equations. And this is the curvature tensor, the Ricci tensor. This is the curvature scalar. And one thing I should have said, I'm going to, unless I put the C's back, C will be 1. And when I put it back, the H bar will be also 1 until I put it back. And I'm using plus, minus, minus, minus for Minkowski. And for sure, I'm going to screw up some of the signs, so it's for you to find out what the signs mistakes are. Okay. I won't screw up the pi's, but I will screw up the signs. So those are Einstein's equations. Now, what is one of the deepest things about GR? If I have black holes, the right-hand side of this equation is 0 for black holes. Right? So what are the equations? For black holes, the Einstein's equations, as you know, is R mu equals 0. Right? Now, what are you used to? You used to is to have a charge somewhere, an electric charge. And then you compute the electric field produced by that charge, which is somewhere. And it has a source. There is something exactly the same as here for the electromagnetic field. And instead of T mu, there is a J. And for example, the static potential, as you know, this is a footnote. The static potential up to alphas, right, is a solution of this equation. There is a source for that potential. There is a source for the metric. But wait a minute. For a black hole, where is the source? No source. So flat space is a solution of these equations. But so is a black hole. And a black hole with mass which is not 0. Where the heck did the M come from? This is a scale invariant. We break in scales. We find a solution. This is not what happens in electromagnetism. There is a source. There is no source here. The scale came out. If you remember, this is an integration constant. And in fact, what happens, which is remarkable, is that GM has units of length. This is a length. And that's how this M came in. And how do you know what M is? Well, we match. We say we look far away. So when we look far away, what happens? So the black hole starts looking like a point. So we're kind of doing an effective theory in which we think, oh, there are some degrees of freedom nearby. I integrate them out, and I match into a localized source. Then it looks like this. We match into this effective theory that gives you the Newtonian potential, and we'll read off who this guy is. But the solution is R mu equals 0, no R mu equals delta. In fact, if you talk to a mathematician and you try to put a delta here, he will kill you. Because there is no solution of that, well-defined solution to that. Because it's a nonlinear theory. You start iterating nonlinearities with a delta, and then you get deltas of 0 everywhere, which blow up in your face. So it's not even well-defined as a distribution. There is the Chicago group of very formal people who are brilliant at telling you, like Bob Wall and Geroff, and Robert Geroff, I'll tell you, this doesn't even make sense to put a delta function here as a distribution. Okay? So how do you do then? Well, you just do an effective theory. I don't care if I have a delta of 0. Okay? I just write some high dimensional operators, just match into a theory that has localized sources. But I have to do some integrating now and modifying what my effective theory means. And this is what we will do. Okay? But this is really amazing. This is one of the few examples in which you get a scale out of nothing. if we knew how to solve the hierarchy problem with gravity, and by the way, a lot of people try this, it would be one way in which you get a scale which is natural out of this, okay? And in fact, I mean, this was for a while also part of the motivation. This I'm sure has some deeper meaning. Maybe some of you one day will figure out what this means.
I'm sorry.
Yeah.
I'm still confused.
Yes, good.
And the singularity, there is still a singularity.
Yes. And?
If you take a black hole solution,
But it's a solution of R mu nu equals 0 with singularity.
there is a delta function.
No, big mistake. Big mistake.
Okay, let's start up.
Yes, the solutions are equations of R mu nu equals 0.
Outside,
And this M is an integration constant. There is no equal delta. There is no delta anywhere. The equations that you write, the Schwarzschild wrote, had no delta anywhere. Now you might think, take a star. Take a star, and then solve Einstein's equation. And you start shrinking the star. There's a smooth limit, and I agree there's a smooth limit, but you have to be careful what you hold fixed, because the pressure and density will go to infinity. So a black hole, I mean, you have a singularity, obviously, when you form the collapse and you try to follow the black hole. But if you want to find the static solution in a space-time, there is no delta on the other side. There can be. You blow in your face. It's a nonlinear equation. It will iterate the delta function. It will have to come. This is curvature, gamma, gamma. Gamma squared is delta of 0.
also Young Mills is not enough function, and anyway,
Okay.
yeah, you're saying it's a different zero.
This is Einstein's equations in vacuum. Do you agree?
No, I'm saying that if you take a black hole solution,
Yes.
you plug there, you say that you get zero.
Exactly. R mu nu equals 0. What was I? So now we have to solve Einstein's equation, form some T mu nu. But as I will tell you, we will use this effective description in which we will look from far away to the black hole. And then we will, even though the T mu nu is 0 for the black hole, we will look at it from far away. And so, so what will happen is that there will be some metric degrees of freedom that go very, very close, very high frequency. We will integrate those out and think about it as a T mu nu. Okay, so there will be some high curvature effects associated with the black hole and short scales that will make it look like what I erased. Okay, and that will be the effective theory. That's how we're going to be able to tell who this M is. Okay. But we will concentrate on that as if there was a T mu nu. Okay, and then we will get back to the case of black holes. All right. So we're going to do linearize. And we're going to span in H. We're going to assume that H is small. Now, this again has no meaning, right? Because I can always do this. I can always take a metric and write it this way. Just plus this minus this, right? What does that mean? So in some sense, we have to say, okay, it's a small perturbation of flat space. So we're going to have our coordinate system. We're going to be far away, looking here at the gravitational waves that come, and so we're going to think about this as a small perturbation of flat space. So we're going to inherit all the symmetries of flat space, and think of this as a field living in flat space. For full GR, this is a little tricky because it doesn't really have a meaning, but it just means that you basically take small coordinate transformations around just the flat space background. Okay, we will have corrections in H bar, so H square, H cube, and so on. And solving for this guy will be our goal. Now you can just plug this in these equations and iterate. Of course, here when you compute the R mu nu, you have to invert the metric, and when you invert the metric, for example, you get an infinite tower of these guys. When you compute here all the corrections to the R mu nu and the corrections to T mu nu, the T mu nu also here couples to the metric, the T mu nu itself, because if you have a matter action and there are derivatives, for example, if you have a scalar field, we have this guy in it, and this guy you also have to span, and so on. Right? But we're going to choose a gauge, and we're going to choose a gauge which is convenient. And by gauge, I mean like there is a residual symmetry So this is generally covariant. You can do general coordinate transformations, which means you can flip, you can shift the coordinates, and then the metric transforms. And if we were in a different background, which is curved, we also have another term, but we are not allowing for that, so we take this to be flat. So we have some freedom as long as this is a small, that's what I was saying, a small gauge transformations or small coordinate transformations, this remains small. So we have this freedom. And then we choose what is called as the Lorentz Gauge. Which is the usual one. By the way, some of you have seen this at the level of like the action of as a field theory. It's the same when you expand this to quadratic order, for example. You can add a gauge fixing term that allows you to invert the propagator. Often people use the Lorentz Gauge. But we're going to use it at the level of the equations of motion, so I'm not going to do that for now at the level of the action. And we're going to introduce, again, this is to simplify our life, this what is called the reverse trace tensor, which just means that we take out the trace. So the trace is minus h. The trace of this guy is minus trace of this other guy. And in this gauge, if you expand these equations, now the R mu has many terms, and you also have to take care of the symmetries and so on. But this is convenient because it allows us to write just an equation which is very familiar. And this is to say, if you haven't seen GR, and you land in here, this is the usual thing with you will have something similar here with the electric source. So this is essentially the same, right? So it's not too different than electromagnetism to say that we're going to source with some moving charges, some field that just happens to have these two indices instead of one, so it's spin 2 field. Well, we start, something I should have said, maybe we start, so it's 10 degrees of freedom, this is symmetric, 4 by 4, but it's symmetric, right? And we're getting 4 out here, so we still get 6, and as you might know, we get 2 polarizations. So we need to cut 4 out still. So we are not done yet. But these are the equations that we need to solve. Okay? The same happens here in the Lorentz Gauge. There is no extra index in that case. So we need still to kill some degrees of freedom, like it's the photon, they also have 2. And this will take us to what some of you might have seen already, which is this transverse traceless gauge. But the whole point now of linearized gravity is to just solve these equations. Or this equation, but there are many components. Right? So we will do 2 things now. I'm going much slower than I expected. One is to say, how do waves propagate? And how waves are sourced? And this will be everything. Once we learn how they propagate, then we need to know how they interact with the detector. So we will first study how they propagate, far some, how they interact with the detector, and how we're going to see this. And then we're going to source them and see the phase of the wave, how is it generated by moving charges, mass. Okay? And that we'll have to do to high order. And then you have to be able to tell me, how do I disentangle the information from knowing this h mu to high level of accuracy? That's a very simple problem. Okay? You could have done exactly the same in electromagnetism, except that since it's a linear theory, it's much easier. Right? But what we will do now is literally what you do in a course in E&M, just a little bit upgraded. And the difference is because it's a theory of space-time, it's an interesting question how we see perturbations of a space-time from Earth, say, like gravitational waves that are hitting us. How do we measure that? What is LIGO doing? Okay? Now, I don't claim I understand everything, but I'll try to give you a flavor. I'm not an experimentalist, and maybe Jesse will, if you ask him later, maybe he talked to people like Ray Weiss and company how they actually work. Because in theory we know how it works, but in practice probably it's nothing like what I'm going to tell you. But we'll get a flavor of how this works, okay? Very good. I'm not sure where to erase, I guess here. Is there any question? Good. So most of you, I imagine, now asking a different question, is up to this point, maybe you need to know some GR to remember that those are Einstein's equations. But if you trust me that this is the end of the game at linear order, then we can just start here and you don't care where it came from. Okay? It's just some field that has two indices in space-time that is sourced by some object that is the stress energy tensor of your theory. If you don't know anything about general relativity, this is what you have written down as your first guess about what gravity should be. Okay? How would you source gravity? Okay? If you knew special relativity, at least. Because you know that your background has two indices. There is a metric somehow. There is an object that perturbs that metric. What kind of equation is going to obey that obeys the symmetries of a special relativity? And then you think, okay, this is mass. The gravity has to do with mass, the equivalence principle. So it's probably sourced by the T mu. Well, you would just try this, and units will tell you G Newton. The 16 pi you cannot get. And this we get from the matching that I told you. The 1/4 pi, they give you the 1/r Newtonian law. This is actually non-trivial because of the issue with black holes. But anyway. But once you reach this point, now the question that you might ask, how many of you have seen radiation theory from here on? You don't like the Jackson much, huh? Okay, this is we're going to do some Jackson. Okay? And then later we'll do Jackson from a completely different point of view, which is this modern approach. Because now we're going to do it the standard way, and later we will see how almost everything we're going to do is translated into Feynman diagrams and amplitudes and so on. Okay, so now we're going to do propagation. So we're not going to source them, we're going to see how they travel. And now we see that we have some remaining freedom that you see if you do coordinate transformations that obeys that the box of epsilon is 0, then the state obeys this equation. So we have 4 more that we can play with, so we can come down from 6 to 2, and this is going to define our TT gauge, or transverse and traceless gauge. Now, in the spirit of the modern approach, we are solving for the metric, right? We're trying to find the metric. From the metric, we will compute observables, right? There should be a way in which you don't have to do any of this. You just compute observables right away from your amplitudes. Your amplitudes already know what the external states are. You only have 2 elicited states, period. So why do I need to do all this? And we will see that we are going in that direction. Maybe we can do everything in a gauge invariant, which we don't have to do any of these choices and so on and so forth. Now, this choice is nice because it simplifies some of the calculations and also makes evident some of the physics. Okay? But hopefully in the future, we're not there yet, but we are almost there. We might be able to do everything without ever going into gauges or even in talking about this metric. And in fact, right now, we'll see in the model approach, we don't compute this metric. we compute, for example, fluxes right away, which is we're going to walk now to solve for the metric, from the metric get the flux. We can go straight to the flux without going through the metric, and that will simplify our life. Also, when we're trying to solve for the metric inside between the bodies, that's a pain in the ass. We might not need to do that whatsoever. Okay. So what I'm trying to tell you, and I don't know how many of you have looked at Lance, for example, Dixon's lectures online, and I did because I like them very much. Is how we go in a direction in which all this gauge dependence and redundancy is actually baggage that allows you to write local equations and solve them, differential equations, but it might not be the right way to do it. Okay? And if I have time, or later maybe in discussions, I can tell you more about how that's happening and how that's having an impact in gravitational waves, and how data is actually driving now a strong interest in doing this in gravity. Okay? Very good. So now what does transfer traceless gauge means? It means that we have some choices to make. We're going to take the trace out, which essentially makes these two guys the same, right? We don't need the bar anymore, right? So if we do this, so we can just say this, right? And we also remove actually I0. What's going to happen is that the Lorentz gauge, okay, I removed this component, not the 0, 0 for now. And now I remove the bar because if I take the trace out, but if you want. But now it comes something very interesting and important. Is that in the Lorentz gauge, if you remove the 0i, then the 0, 0 has no time dependence. So in the 0, 0, dot the 0 from the Lorentz condition. Which means that we can divide this in two pieces. And this will be also part of the genesis also of how the effective theory is going to come about. Because what this is telling you is there is a radiation part which does not have, I'm going to call it H, even though this is the big H, I'm going to keep calling it H, just abuse of notation. I should call it differently. But I'm not going to put twiddles all the time. In fact, in the papers and the effective theory, sometimes we put bars on it to say radiation. But the bar is this guy now, so I don't want to confuse you. But there is also a bar that I'm going to call big H, which I'm going to call potential, because I'm going to start looking forward into this distinction between the gravitational field having a piece which is the on-shell radiation and a piece which has to be there, which is sourced by the whole binary. There is a 1/r potential that has to be there as well. So if you look far away, say, from the binary, that lambda that is in there is the radiation field, but there is also a part which is just the Schwarzschild solution. That thing is gravitating. Okay? You can take a particle and it will have a geodesic deviation in that background of a binary. Okay? A neutron star could be sitting in the middle of the galaxy, right? And you can orbit around it, even though the neutron star inside is a lot of things. It's moving and so on. So even though there is motion, there is dynamics, there is also or a pulsar, right? There is also a static component. So that static component, that 0, is just the background, like the Schwarzschild background. So it means that if you're looking far away from the source, there is a piece which is the static potential, and there is a piece which is the radiation. This piece is not 0, but it has 0 dot, which it has to, right? This piece is 0, so we take it out. So then it becomes 0 for the radiation. And now we just concentrate on the radiation. What does that mean? That means that this equation could have been Laplacian of H00, right? Or it could be box of the radiation field. Okay? So in this case, then now we're going to solve for the equation, we remove the bar because we took the trace out, and this is Tt equals 0. And this is propagation. This is on-shell propagation. By the way, why do I insist on this distinction here? Because what is most important is the potential or the binding between the objects. You will think that the potential generated by the binary as a whole doesn't do much, right? It's just the gravitational field produced by the binary. And then there's the radiation. But the radiation is propagating in that background. So to be consistent, as we'll see here, and you'll see how the diffractive theory works, there's a split of this metric field into a radiation and a potential, and that potential also enters here in the background. So this background that I'm saying is flat, I'm actually lying. Here is the radiation moving also in the field of this potential. But at linear order, that doesn't matter. They don't talk to each other, so it just goes for the right. So I don't care. But at nonlinear level, then it does matter. This box will get a contribution that knows about this H. And that is beautiful. That changes everything. This is something that doesn't happen in any other theory. Well, maybe Yang-Mills. Although you don't radiate glue. So GR is unique in that sense, right? Is that the propagation happens, is the binary, in a background that can also perturb the propagation. And these things are called tails, like tail effect. Some of you might have heard about the memory effects, which is the interaction of the wave with itself. So in that case, it's like nonlinear effects. This is like a radiation mode. This is what we call a potential mode. So ignore the memory for now. The tail, what is called tail effect, if you read a paper and people talk about tails, it just means that the radiation can scatter off the background. And that can introduce time delays. That can change the phase. And that's a very important effect. It's so important that it played a crucial role in the recent derivations to the gravitational waveforms to the higher levels of accuracy, which unfortunately I won't tell you much about these subtleties. Today we know, for example, the binding energy of a system up to 4 post-Newtonian order, which is order Vc to the 8th. This is my son's. Sorry. Anyway, I taught my son the infinity. He has to do the 8. He doesn't like it, so now I do the 8s like infinities. To the 8, okay? So this is next to leading order, or for loops, as we'll see when we see the methods. This is where we are right now. And these effects play a crucial role, okay? Why do they play a crucial role? Well, they play a crucial role because they introduce divergences. And those divergences are associated also with this split that we do in between potentials and radiation modes. And in effective theory, what's going to happen is that we're going to have like renormalization groups, evolution equations. So what's going to happen is that the radiation could be like trapped in that region. And then what we mean by the mass could be renormalized. So the binding energy gets renormalized by these effects, which means the binding energy of the system is not just produced by the forces between them, it's also produced by the radiation through these tails. We've seen that before. We've seen them quantum mechanically. A long-distance radiation changing the binding energy. It's called the Lamb shift. And one of the problems with the Lamb shift was all these pesting divergences that people didn't know how to calculate. And this is also one of the reasons why this calculation was subtle, because at that order, there's a Lamb shift, purely classical Lamb shift in the gravitational potential. So this is very interesting and it's very important, but we will not go there now. Okay? But there's a logarithm, there's a beta logarithm, classical beta logarithms in the binding energy at this order, which is exactly the same as the Lamb shift, but no H bar. If you think about don't let me talk about that. What the Lamb shift really is, it's really, really beautiful piece of work. So we want to solve these equations now in this case. This is very easy because this is, we know what the Green's functions are. So this is just a propagating wave. So in this case, say you propagate in the C direction. So say this is in the C direction. The wave is propagating into the plane of the board. So we have these two polarizations. So this is a matrix. And these two polarizations are often denoted as H plus, is traceless, and H cross, and the rest is 0. I don't want to put all the zeros, okay? 0, 0. And then it oscillates. With C equal 1, right? So if you didn't know any GR, but you knew that gravity was a theory of space-time, that you could have guessed also from special relativity, and Einstein was actually playing with this idea as well, you would have written, inspired by this, an equation like this. You would realize that you have too many degrees of freedom, that you still have some redundancy, and therefore, which the redundancy, by the way, you could have had. Einstein had the equivalence principle and diffeomorphism, what ended up in diffeomorphism invariance, the change of coordinates already, so you could have also landed here, which, by the way, can also give you the form of the action, like Feynman did. And then you would have solved these equations, you would end up here. So this is not necessarily GR. This could be just linearized gravity in many theories, okay? So how do we test GR? And honest GR is because we correct this, well, nonlinearities that are given by general relativity, also by seeing the event horizon telescope and seeing a hole there. Things like that give us confidence about general relativity, but at this level you could have written this theory without ever talking about curvature. Okay? These two polarizations are called the plus and cross. They change the space-time. I don't know if this is illuminated or not, but if you write the metric, the metric allows us to define the line element as you do in a special relativity, but now we have a curved space. This is curving space and time. Gravity is a theory of space-time. And this is the perturbation, so this is flat space. What we just learned is that this is flat space, and then we have this correction, which stretches in one direction and contracts in the other direction. For example, in the x and y, and also in what is called this cross, dx dy. So this is what we do into space-time, and we will see how this can be detected. But what is happening intuitively, you see, is that you have a circle of a ring of masses, right? That's usually what demonstrates. Then you start stretching as this wave oscillates. And you go through the period, you start bloop, bloop, and the other one goes in the cross direction. Right? Now, you have to be careful, because this is one of the things that confuse me and everybody for a long time, and still is kind of you have to really get your head around it, right? Is that the x and y means nothing. They're just coordinates, and we choose a gauge, this TT gauge, and those are the coordinates. That does not mean that this is a change in x and y. It's a change in the length, in the proper length, which is what we measure, right? Because as we will see now, what happens to the coordinates? The coordinates don't move. The coordinates move with the wave, as we will see in a second. So actually, the length between the coordinates stay fixed. So it's really the proper length that is changing. Okay? Where can I erase? Up there. But we will see already that the proper length stretches in one direction and the other contracts, and when this changes sign, the cosine it does the opposite, and so on. So the idea that we're going to get at is that you can tell, of course it's much more complicated than that because the wave doesn't really come necessarily this way, right? And as we will see, it has to do also with the wavelength. Well, there's a split of scales again, right? There's a typical lambda of the wavelength, but there's also a typical size of the ring that you can make on Earth, okay? So this will be 4 kilometers, say, for LIGO. And there's a wave coming that is modulated by some k, right? Omega. That better be long enough so we can actually see this guy. As you will see, it's an approximation of flat space-time, right? And many of the subtleties about how we're going to observe this wave in this background are not there. We'll see what I mean. But what I'm trying to get at is that when we have LISA, say, in space, that's like many, many kilometers apart. I forgot how many, but it's of the size of the sun maybe, orbiting around it. Then it becomes tricky, right? Because it won't travel 4 kilometers, it will travel much longer. And a lot can happen in that time it takes for the laser to come back, okay? If the waves are much shorter wavelength. But the idea will be that if I have a ring, and I somehow can tell the proper distance, and again, we're in GR. We don't measure instantaneously the distance at a given time, t. That's impossible. Somebody has to yell at you, oh, yes, I'm here, right? I can send a photon, but the photon has to travel up and down. So this is not an instantaneous, static, meaning a time t. And then at the next time, right? It's not that I can make that picture. I'm not looking from above. I'm not God, right? So what I do is I send a photon up and down. And when the photon comes back, if it takes a longer proper time, right, then there will be a phase difference, and that's what we will observe. Okay? So actually I have to have some space-time diagram in which the photon goes and comes back. Okay? So we're going to measure that, and in there is a background of the wave, which is actually, if this is 4 kilometers, if it's actually comparable, then it's problematic. At what time or where, which distance I'm measuring. So the good thing that allows us to disentangle much of this is that this wave is really long. So we can think about this like essentially flat space with a very small perturbation, long wavelength perturbation. And in fact, as we'll see, LIGO, they will send the light back and forth many, many, many times. So they can actually build up more than those 4 kilometers. It goes like, I don't know, 100 times. So the length actually is not 4 kilometers, it's back and forth, because the wave is not changing much. Okay? And that's one way in which you can enhance this H that we will see is immensely tiny. Okay? And this is something that also you're going to have to wrap your head around when we see how small this can be, is that in LIGO, which has 4 kilometers, a change in the proper length on 4 kilometers of an H, which is of the order of 10 to the minus 20, will give you 10 to the minus 17, 18 meters. And you can ask Jesse how small that is, and how we can prove that, if we can even get to that scale. Okay? So now you might ask, how the heck are we observing this? Okay? And this is one of the beautiful things about physics, is that you have to be careful about what those numbers really mean and what you actually measure. Okay? Very good. So now, let me tell you a little bit about how this interferometer works, and let's solve the equation, for example, in this case for the geodesic equation, and then we will see what I just told you about how if you at rest in this coordinate system, you will remain at rest. You will move with the wave. How this is not what we observe, but what we observe is really the proper length, or the time that it takes that photon to go up and down. Okay? Good. How many of you have seen some of this already? Many of you, right? In this fashion, the same way? More or less, okay. All right, so those of you who are bored, hold on. Hopefully we'll get to more interesting physics soon. Okay, so then I'm gonna tell you a little bit. I'm not gonna get to the source. Okay, so today I'll finish this and tell you a little bit about how the detector works. And then next time we do the sources with linearized gravity, and the last two we will do the effective theory approach. Or maybe we start next. Maybe I hurry up a little. We'll see how we go. Okay, so we have this TT gauge. So we can look at coordinates, and we have, for example, a particle that is moving, and we have the coordinates. There's a parameterization of that world line. We can also use the proper time if you want. We can use any affine parameter. And you know there is an equation that tells you in that space-time how does the particle moves. And remember, something that you probably know but don't quite appreciate, perhaps, is that the motion on Earth is mostly dominated by the Newtonian potential, which is the 0, component of the metric, which means it's time. So it's really your clocks which are making you fall, right? It's not space, it's time, right? It's also super misleading, this thing that we do with the black hole. But anyway. So here we will see how time is playing the role, how this TT gauge is doing to time, such that we move with the wave. And we're going to assume this is the geodesic equation with this gamma, the connection, which, if I remember, goes something like this. Beta number alpha, half. Now, in flat space, this is 0. So the connection will come at a linear order from flat here and h here, right? And we're going to go on to compute this in the TT gauge. Stop running. To know what happens to that coordinate, to that parametrization of my world line on those coordinates with proper time. Okay? This is not necessarily how this moves really, like physically, but those are the coordinates that we're using to parameterize the motion. Now we're going to assume that you cannot be completely at rest in space-time, but we can assume that we are initially at rest. Then the spatial components are going to hit the velocity, which is 0. So only the temporal part is going to matter. So from this guy, we just want this guy. Which, by the way, in Newton, the 0, component is the metric, 0, which is the Newtonian potential, and it's the gradient of the potential that gives you the acceleration, and that's how you move. But in the TT gauge, this is the 0 of h0i. The up and down indices you fix because the signs are going to come out wrong because of my minus convention, but I just don't want to waste time on that. Minus di, and this is 0. And therefore, then the particle doesn't go anywhere. Of course, we're talking about space, right? Of course, you move in time. You cannot stay put in time, right? But you can. not move in space. And this I did not specify anything. So if I take two geodesics and I look at the distance between them, if each point doesn't move, the difference doesn't move. Okay? But we can also see that if we do the usual geodesic deviation, so if we look at a point x and x plus a little bit, and we compare the two geodesics, and we look how this separation changes with time, so the equation for the geodesic deviation is very conveniently written in terms of the covariant derivative and the Riemann tensor. Let me write this correctly. New gamma. And then the velocities. Gamma. And do this as an exercise. You have to realize something here, which is going to be very important. This is how you understand the physics of GR, right? How the coordinates are a little bit misleading. Had I computed this in a different gauge or in a different set of coordinates, I could have gotten a different answer. For example, what if I go to the free-falling frame? What if I go not to the TT gauge, but to the Fermi coordinates? That's the coordinates we use on Earth to say this is 1 meter, 2 meter, we measure, right? So it's a frame in which if I look at the connection at a given point, I can set it to 0. This is the free-falling frame. And the metric is flat space plus curvature effects, some curvature length square. So the first derivative you can kill, but not the second derivative, right? This is a physical frame in which we see curvature effects. Like if you're in cosmology, you see the Hubble curvature, but otherwise you see flat space. So what happens in this frame is that I could have done the same thing. Now the coordinate distance, unlike the TT gauge, in which the coordinate distance does not change, and that's what the exercise I was going to ask you is like, now go ahead and plug this in here, and crucially, there is a connection here that will not vanish, and it will cancel, such that this equation is also 0, because we know that those points don't move in the TT gauge. But if I go to a free-falling frame, the connection is 0 at that point, and there's curvature. But now it turns out that a linear order, the curvature tensor, is invariant under these transformations. So I can compute in any gauge. I compute in the TT gauge if I want. And in TT gauge, this is actually not 0. What is 0 is this equation, and there is a gamma in here, and that's crucial. Okay? But in the free-falling frame, the gamma is 0. So I just need the curvature, and the curvature I can compute in a linear order, in any frame. And then if I do the one that survives, which is the same as in Newton, here, right? This is HIJTT. There are 2 zeros, so 2 zeros. And half. So the Riemann is not 0. The geodesic deviation is 0. And the key is this equation. We are in a different frame, right? And now you see what's going to happen to the actual physical length now in the free-falling frame, which is a coordinate difference in this frame, because the effects are second order. And this, again, is very important that this curvature is small. And this will be associated with the wave that's going to hit us. What is the curvature scale of that wave? Compared to the distance between the two geodesics, which is the LIGO detector, right? And this equation is telling us how this oscillation in the curvature is also the oscillation that we will see in the detector. And maybe we can do it as an exercise, because I'm running out of time, that you're going to get the exact same equation. Now, what we learn is that the coordinates do not move in TT. They do in the free-falling frame. And we can rederive exactly this equation by now looking at the proper length, not the coordinate length, but the proper length here. So you have to take a square root here to get a length. When you span the square root, you get a half. And that's the half. Okay? And then you get h, and then you're going to get an equation, which is going to be how that, so you're going to get an equation in which the length say in the x direction, will be L plus a half, say with the plus polarization, the wave comes like this. Okay? So if I take derivatives, the derivatives are going to hit here, right? If I take two derivatives, say, this goes away, so I get a half h plus dot dot L. But the leading order L is like S, because the deviations are quadratic in the metric. Say this is how the proper lane changes in X, okay? And this is the TT gauge. This is the same equation that you get from this equation here in the X direction for the physical free-falling frame. Okay, they're equivalent, they're the same physics. Here you see it as a proper length shift, the physical length changing, in this case with these coordinates. Here you see it as the physical coordinates in this free-falling frame that you can associate with actual measurements, up to these effects that we have to see that are small. But using the fact that this can be computed in any gauge, in particular the TT gauge, and it's the same value. And this is the double dot. And then you get acceleration equal h double dot, which is exactly what you get here. Notice that there are quadratic terms that you're neglecting. And this now looks a lot like what you'll see if you have, for example, some pendulum. The wave comes, and what it starts doing is starting like a force that is oscillating, right? Now, how we're going to see that is part of the whole problem of how the LIGO detector works. Because this is all fine. 2 minutes only. I'll come back to this because it's very briefly before we start tomorrow. But one interesting question here is like, oh, this is all fine. If I have this ring of matter in free-falling space far away from everything. That's awesome, right? If I could really do that, and in fact that's sort of what Lisa will try to do with free-falling detectors, right? We are not in a free-falling frame, right? In fact, we're stuck on Earth, so this is all fine, but it's not true. There are corrections here. There are corrections here because we have a G on Earth, and we have a Coriolis form. We're also rotating. Okay. So these effects have to be factored out in here. And then we have a problem. How are we going to see this effect, which, I mean, I'm not going to get ahead of myself too much if you have seen this already. These are the order of 10 to the minus 20, which means h times L for 4 kilometers is 10 to the minus 18, 10 to the minus 18 meters. How the heck are you going to see that when the surface of that guy, of this pendulum, with just Brownian motion, because you don't have a perfect vacuum, or the radiation pressure that you're hitting with the photons that are going to go back and forth, it's already way bigger. You don't even know, I mean, the size of the proton is 1,000 times smaller. So you don't even, where do you hit? You hit here, you hit there? How do you aim? Well, what are you doing, right? I actually don't know the answer. I can just mumble words, okay? Because this is remarkable. So there are a lot of tricks. But I still find this extremely fascinating. So many tricks that you can do, for example, so what is the background? The background is what I just told you. Brownian, because you know exactly vacuum, and pressure from the radiation, okay? So you've seen this already. So there is a radiation pressure that tells you that you're not going to go higher than a kilohertz. And you need to also isolate from this G, which is what we call the seismic wall, that shows up around 10 hertz. So you see what I'm getting at. You're not going to measure this exactly as you go and put a rod in there. The atoms in the rod are bigger, okay? So you see this through this phase shift difference. And remember, we're also going to send the photon back and forth many, many, many times. We have a time series that takes some time. It's not just instantaneously. So we also integrate over time. And we see it in frequency. We cannot even imagine beating gravity. But gravity, the perturbations in the gravitational field are very low frequency. So if you look at higher frequencies, you have a chance to beat this guy, the G. Now, how can you beat this guy, the radiation pressure and the vacuum? Well, make the best vacuum you can. and also realize how you can use the laser, the power of the laser, and so on, and where do you get the best, is around between 10 hertz and a kilohertz, and it's around 100 hertz that you have the most sensitivity in your detector. So that's essentially the LIGO band, and this is an H of the order of say 10 to the minus 20, and this is in frequency. So look at frequency. You cannot possibly measure this at 0 frequency, it's static, right? Because G will kill you. But if you look at things that are oscillating at a specific frequency of around 100 hertz, you might have a shot at this 10 to the minus 20. You have lots of tricks. You have many pendulums, for example, because if you rattle this guy up here with these radial motions, this guy here is very stable. So then you have many, many guys hanging with each other and so on. So there are many, many tricks. You send the light also back and forth many times to build up the phase difference that will come from the distance, and this will be associated with the time that it flies the wave. Do I want to say this now? Okay, let me not go into this right now. But the point is that what object we're going to detect that create these oscillations in distance that we see as a phase shift in the wave, in the travel time of the photons up and down, which, by the way, notice this goes this way, but if I have a photon that goes up and down, it's actually twice. So this twice this, so it's H plus L in the X direction. In the Y direction is minus. So actually it's twice the difference, right? Because you go this way, and you go back and forth, and each one of them is twice, and then the difference is like it's shorter, minus and plus, so it's twice HL, what the difference in time, which you want to observe, and that difference in time is multiplied by n. Okay, and then you have a laser wavelength that's nanometers or whatever, and then you get your phase difference, and this is what you try to measure in this band. That's the hope. Another question you might ask is like, what produces a 10 to the minus 20 that peaks around 100 hertz? And this is what we'll see when we source these waves. How the actual black holes that we observed actually were around 100 hertz is when you have the most signal to noise. The first, I forgot what, 300 I think it was the merger frequency of the first black hole collision, this GW15 or 914, that you see something like this. This is the amplitude of the wave as it sweeps through the detector. Now, another tricky thing, I really don't have any time, I had to cut off, right? It's like, you'll see these pictures in frequency space, not in time. And you see the wave, the amplitude of the wave actually going down, not up. This is counterintuitive. The first time I saw this picture, I said, well, what the heck? How is it going down and not up? In fact, it goes up a little bit towards the end merger, because what I want to tell you that the down is really just the linearized part, is that you're in frequency space. And when you do like the saddle point approximation to calculate the phase, right, and you Fourier transform, you pick up a factor of, I think it's 7.6. So actually decaying even though the amplitude in time is going up. But in Fourier space, it looks like going down. Okay, it's just a trick. And then you see the signal that really merges around here, 100 hertz. How do you get that merging frequency? Boy, just the cutoff. If you have a typical 10 to 100 solar mass black hole, and you compute the GM, the R-Schwarzschild, and you compare to frequency 1 over that, it will give you around 100 hertz. And that's why people thought, astrophysical black holes are around this scale. They merge around 100 hertz. I can make a machine that does that and detects it. Neutron stars, unfortunately, they merge somewhere here because it's smaller mass, 3. So the frequency is actually 2 kilohertz. They merge here. But we get a lot of signal in the detector, which might not be as loud, but it's longer. So by doing high precision, we can get a lot of information out of it. And that's what we want to do. Okay? Let me stop here, otherwise I don't stop. Thank you. Shall I answer a question or we just stop? Do we have any question? No? It's all crystal clear?
We
scale.
Very sensitive case, sorry. If I understand well, conceptually, you're seeing it in a different manner as a vacuum solution that breaks scale, with a breaking scale, like we're used to it, for example.
How do you select that solution? That goes back to that question, right? If you remember when you're doing the math, the algebra, then you have an integral. And then because it's units of length, you have these boundary conditions and so on. This is r mu nu equals 0. And when you go and solve for that integral because of the connection, you get plus constant or length. And that's when the m comes in. It's some integration constant. It doesn't have to be 0. So it could be anything. It could be m, the black hole. Of course, then you find there is a singularity. The curvature itself is blowing up as you approach 0. That is indeed the case, right? In that solution, and it's not an honest. Okay, so the question that he's saying, or what he's saying, is like, what's happening there, right? Because you're trying to solve r mu nu equals 0, and but we're saying that the point r equals 0 is an honest singularity, right? Where the curvature goes to infinity. Right? So what's happening? Well, in theory, in practice, you can say, well, it's true that you kind of have to cut this off if you want, because you don't really know that scale. But that doesn't mean that there is a delta source. It's not that I'm solving everywhere in space-time this equation. I'm not. I'm solving this equation, and I notice that there is a problem in that solution as I approach 0. But it's a solution that solves this equals 0 everywhere. Not this equal delta, and it's a source of delta, and this problem is the fact that I have a delta source. No.
It's different than the Schwarz one.
Sorry?
It's different than the Schwarz.
Schwarz is, when you, in GR, which equations do you write?
This one.
This one.
But I intended for the exterior part.
Yeah, it's always a solution everywhere, except at the r equals 0. But it's not a solution of this equation. That's what I'm trying to emphasize. It's not a solution of this source by something on the, or, but then you can say the following. What if I put a T mu nu, there's some distribution of matter, and then I start collapsing, right? And then I found the solution. But then what happens is it's smooth, because now I have to match with the interior. And then as you start shrinking, and the mass is defined as an integral, right? As I start shrinking, the pressure goes to infinity. And so there is the Chandra-Sekhar limit and so on, right? You start collapsing, there is nothing that also will stop you, and then there is nothing that can stop you from collapse. Now, what is the endpoint of collapse? Nobody knows. I mean, but we do know that the solution, the Schwarzschild solution solves these equations everywhere outside, not the delta. So the delta you can cook up by saying, okay, I'm going to say, I don't know. So I'm going to say this is the solution. I don't know what happens very, very short. So I'm going to call this very, very short and longer. And then I'm going to put this on the other side. And this could be also sourced by the T mu nu, but r mu nu short. And this now, I can say, okay, this is very, 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 very short. It can look like a delta function. And then I'm saying, far away, if I'm doing this effective theory, the solution of these equations, far away, look like this. Sourced by some short distance that I don't know, which I can, as an effective theorist, I can treat as a delta function. And this is what we do also to look far away to solve for what the m means. Right? We match into an equation that resembles the other thing. But if you try to solve this equation, I'm not saying anything, I mean, it's deep, but maybe not that deep in the following sense. If I try to solve this equation, this is now a T mu nu. If I put this T mu nu and I iterate, I'm going to get delta of 0, which is infinity. I don't even get the Schwarzschild solution. There's deltas of zeros in my face all the time, everywhere. Not that r equals 0, everywhere.
Okay, and so that's my point. If you don't reach the Schwarzschild solution, so it's a different way of seeing it.
You're saying you split long and short, and then the short you treat as a localized source, and then you solve for long, then you get that solution where m is actually, you can really treat like a charge. You integrate like Gauss's law, and then you get the m as just the charge, the same way you do it in QED.
Right? Can I be sure that the only solution of m equal to 0 everywhere is a black hole with its singular
That's a very good, so whether the black hole is the only solution to this equation?
all the characteristics, the singularity, the horizon, and everything.
Can you rephrase the question? The question is the black hole the only solution to this? And is that
The only solution that breaks scales for this.
Well, we know for a fact that there is uniqueness theorems about solutions which are static or stationary, if you want, for the Kerr solution, which has, like, for example, some rotational symmetry, axis symmetric, and so on. So there are some theorems like Hawking, Carter, and Penrose, and I forgot a bunch of people, that they show that these are they're unique solutions, right? And I cannot tell you much about how this works. It's pure GR-ology. But I can tell you that if you put a delta function here and you try to solve these equations, you're going to run into problems. Very quickly, the thing is going to blow up in your face. So you will not find the Schwarzschild solution anywhere. But you have this split that you can do, which is also what we usually do. We're looking very, very far away from zero, or from the Schwarzschild radius, say. There are modes in here of the metric that I don't know. I'm looking far away from the solution. And then this equation has long and short. This from far away looks like a localized source, and I can solve this far away, and then I can read off, because it's the same solution. It will match to this solution that is everywhere fine except for r equals 0. We can find what the m means. Okay? Maybe it's not that deep. But the point is that there is no scale in these equations. I mean, come on. We have to say this is, did I erase? What are Einstein's action? So the action is the square root of GR, right? What are the equations? There is no matter. What are the equations that come out of this? R mu equals 0 in 4 dimensions. There is no delta anywhere. Where is the delta? These are the equations, period. Find solutions. Go fight in the first war in the trench and write the solutions. That was the guy did, right? He didn't even know what a delta was. Delta, I mean, distribution, what the heck is that? The guy found the solution. And they realized that not just flat space had a solution. And there was not just one singularity. There was the Schwarzschild singularity they didn't understand either. It was not a physical singularity, so we don't know what happens exactly at r equals 0. But you can find solutions which are completely fine except for one point. And there are solutions of this equation. Where did the scale come from? In fact, this scale invariance is still there. In some sense, it's related to the fact that when you measure the gravitational waves, you don't really know this m and the fact that there is the redshift. So you don't measure just, so what we measure at the detector, the m is not necessarily the same m as the m of the source. It's redshifted. And then you have to have some idea what the redshift is to really know what the masses that we observe here versus the masses at the detector. So that's also tricky with the fact that these are the equations that you're solving. Right? Cool, now you have something to think about. All right, Shasta? Okay, thank you.
Be around this afternoon?
Yes, I will.
Cool, because I want to eat them.
Sure, sure. Did the recording work? Ah, okay.